Welcome to the lecture 13 of Financial Econometrics, and in this video we are going to cover the interpretations of certain elements or different types of regression model. So moving towards the contents, we will try to understand or interpret the R-square and adjusted R-square. We are going to understand regression through origin, and then we will see how do we interpret the variables when they are on different scale. And finally we are going to understand what standardization is and how do we interpret the coefficients when we have standardized variables. So starting with this concept, we are going to build the concept of R-square using this example. So starting with this example, we always discuss the example of salary. So imagine we collected data of certain individuals and we computed their mean. And let's say the mean was 5,000. So what would this mean tell us? Remember, this y is the salary variable. Let's just say y bar, which is mean, is 5,000. This would tell us that on average the individuals that we included in our sample would have the salary of 5,000 rupees. Now, not all the individuals would have the same salaries. Some would have higher salary, so these are the specific individual, these dots. Some would have a lower salary than our expectation. And this dot, this yi, is a specific individual whose salary is, let's just say, 10,000. It is different from our expectation or mean. So why do we run regression? Besides the other reasons, one of the reasons is to find out the factors that would explain this variation in salary or this variation in our dependent variable. So there is this specific individual whose salary is 10,000 and it is different from, you see this curly bracket, this part, this variation between the salary of this specific individual and our mean is what we call total variation. Remember, it is the difference between yi, this observation, the salary of this specific individual, and y bar, this is the mean of this sample. So yi minus y bar, this is the total variation, the difference between the value of this specific individual and our expected value or the mean value. This is the total variation. What we did, we introduced, let's say, an independent variable. Let's just say in this case it is education. We are trying to explain this variation between salary. Why someone is having higher than expected or higher than mean salary and the others are having a lower than mean salary. So why is there this variation in the dependent variable? From one individual to another individual, from one company to another company, from one year to another year. So there is this variation. So we introduced our education variable, which is the independent variable, and we are saying that some people having higher education would have higher salary. So according to this, when we introduced the independent variable, we did some calculations, we interpreted the regression, we draw the regression line, we predicted the the expected salary based on our model which have only one variable, which is independent variable, which is education. We expected that someone with this level of education, this XI level of education, would have a salary of say 7,000. Now this difference between the salary predicted by our model and the mean, so this y cap is yi cap or hat is the value predicted by our model minus the y bar, which is the mean. This difference, this variation, this part of the variation, let me highlight it. This part of the variation is due to the variable that we have included in our model, or due to the regression, or what we call the explained variable, explained variation. Right? So this part of the variation is explained by the variables that we have introduced in our model, but this part is still unexplained. We do not know that although this model, which have education as an independent variable, predicted that this should be the salary of a person whose education is XI, say 10 years of education, but why this specific individual still have a salary different from our predicted salary. So this is the this difference might be due to some other factors. This is the residual or leftover part. So this variation, this part of the variation, if this is the explained variation, this part of the variation is unexplained variation, what we call residual. So now what we have understood is that there is a total variation, and that total variation is divided into two parts. One is the explained variation and the second is the unexplained variation. And the unexplained variation, it isn't written here, but let me write it. The unexplained variation is yi minus y hat I. So now you can see this, this is the unexplained variation. So what we can say is that total variation is equal to explained variation plus the unexplained variation. And due to some reasons which we will not cover in this lecture, we take the square of these variations, and some part of this reasoning had been developed, had been discussed when we were developing our OLS formula for this coefficients, and we also had an exercise on that. So this so due to some reasons we take the square of these variations. So now instead of total variation we have total sum of squares. So we have this square over it, then we have explained sum of square, and then we have residual sum of square. And if total sum of square is 100% or 1, it is in, now we are converting it into ratio form, then the ratio would be explained sum of square divided by total sum of square plus the ratio sum of square divided by total sum of square. This both should be equal to 1. That would be total variation. We know that explained sum of square is yi hat minus y bar whole square. And divided by total sum of square is y minus y bar whole square. And the residual sum of square is summation of this residual, and residual is equal to this square divided by the total sum of square. So if we find the formula of r square, then r square would be the percentage or ratio of the explained sum of square divided by the total sum of square. Remember, this part is the explained part. This is the explained variation, and if we wanted to give it a percentage with regard to total variation, then what would we do? We would divide this with total variation. So we have explained sum of square divided by total sum of square, their formula. Or we can simplify it, or we can write it in another form, which is r square would always also be equal to 1 minus residual sum of square divided by total sum of square. Remember, this ESS divided by TSS. So we have algebraically converted this into this formula. So what this r square tells us, it tells us the explained part of the variation. What part of the total variation is explained by the variables that we have included in our model. So just in case if we get the r square value of 0.60, that would mean that 60% of the total variation, this is the total variation, 60% of this total variation, which would be this part, this part would be 60% if we get the r square value of 0.60. So 60% of this total variation is explained by the variables that we have included in the model. The rest 40% is unaccounted for. We do not know what that rest 40% is, this rest 40% of variation is due to. So this r square is also called coefficient of determination, and the simplest simple interpretation is that the variation in dependent variable due to the explanatory variables included in the model. Now one variation of r square is adjusted r square. Now one problem with r square is that, as we in previous example, we just had one explanatory variable, one independent variable, and we like to keep only one independent variable when we are discussing these concepts, just for the sake of simplicity. But in real world, there won't be one variable explaining the concept. So in case of salary, there won't be just education that would determine the salary. It would be experience, it would be socioeconomic factors, it would be the person's IQ level, it would be the country that or the city that person is living in, and there would be 10 of other factors also. So there would not be one explanatory or independent variable, there would be tons of independent variable. Now the problem with r square is that as we increase the independent variable, the r square always increases. Even if the variables are irrelevant, the variables that we have included in our model, the independent variables that we have included in our model, even if they are irrelevant, even then the r square would tend to increase. That is because of the formula that we have. So what we do is, when we use the statistical packages, it also gives us the adjusted r square, and the adjusted r square value would be always lesser than the r square value, and that is because this adjusted r square value would be adjusted for the number of variables, the number of independent variables that are included. So it would increase as we increase, the adjusted r square would also increase as we increase the number of independent variables, but it wouldn't increase as much as the r square would increase. So it is somewhat a better measure as compared to r square. Now one more thing that you should be careful of, that when you are using different models, say for example you used a model where you had an independent variable of education and you had income, and then there was a second model where you used the log of salary instead of salary itself, or some other independent variable, no matter what the independent variable is, then you shouldn't compare the r-square of this model with the r-square of the second model. That would be that wouldn't make sense, right? So when comparing the r-square of different models, you should keep in mind that dependent variable of those models should be similar. So in this case, you would say that both models do have the salary variable, but in case of the second model, we are taking the log of the salary variable, so the variable is transformed, it isn't the same. So you should keep in mind that the r-square should be, when comparing the r-square of different models, the dependent variable must be similar. Moving to next concept, which is called a regression through origin. In regression through origin, the intercept term, the alpha term, the concept term, or what we call the beta naught or beta 1, would be absent or it would be 0. So remember, we always had this model, y is equal to alpha plus beta x plus the error term. These subscripts, we might have discussed it. These subscripts represent the type of data. Remember, we had cross-sectional data, we had time series data, and the panel data. When we have a subscript of just I, then that means it is a cross-sectional data, or we just have different cross-sections. If it is a T, then we have a time series data, and if we have both I and T, then that means it is a panel data, right? We both have cross-section and the time factor. Okay, anyhow, coming back to our concept, remember we always had this model where there was alpha, and what alpha meant was that it was the y-intercept, right? And it would mean that if the x variable is 0, this is 0, if all the independent variables would have a value of 0, then what would be the value of the dependent variable? This is our y dependent variable. So if in this case, again, education is our independent variable and y is income, then this y-intercept would mean that even if someone having 0 education, by 0 education I mean the systematic education that we have, the formal education that we have. So 0 years of education, then that person would be earning this much of salary, this much of income. This was the y-intercept or alpha. But in some theories, this theory would suggest that the y-intercept should not be present, the alpha should not be present. So in those cases, the regression line would pass through the origin. So in that case, let me draw it here. This is how it would look like. It would pass from the origin, and origin is 0. So in that case, that would suggest that if someone have a 0 level of education, then his salary would always also be 0. It wouldn't make sense in the case of education and salary, but in another example that we would just discuss, it would make sense. There is a model in finance which is called capital asset pricing model, or CAPM. And in CAPM, the theory suggests that the alpha would be missing. We cannot discuss this theory in here, but if you want to, you should search the theory and understand, watch some YouTube videos. It is related to finance, and you might have studied it in your finance related courses. So what this theory suggests is that the return of a stock is purely dependent on the systematic risk of a stock. This is RF. And there is no alpha. It purely depends on the systematic risk of the stock. So this is the CAPM model. So CAPM model suggests that the regression line would pass through the origin. So in this types of model where theory suggests that there would be no constant or the alpha term or y-intercept term, In those cases, we would have a regression through origin. And when you are using the statistical package, or just in our case we use Stata, there would be an option when you open the dialog box of the regression, and we would discuss it when we use the software. There would be an option to compress the constant term, and when we are going to use the regression through origin, then we must use that option. Okay. So next we are going to understand the scaling and the unit of measurement. Okay, let's just say we have two variables. The dependent variable is gross private domestic investment, and the independent variable is a GDP. These both, the independent and the dependent variable, are measured in billions of dollars. Now when we run the regression, we use our formulas to find the values. We would get these values. Currently we are interested in, say, these values. So how do we interpret these values? This 0.25, it means that when the GDP would increase by 1 unit, the gross private domestic investment would increase by 0.25 units. Now that isn't quite meaningful, right? Because we have the data in billions, what we can do is, while interpreting it, we can say that when the GDP increased by $1 billion, the gross private domestic investment would increase by $0.25 billion. So the point is that what units should we use while interpreting the variable, while interpreting the coefficients? The variable would depend on the unit of measurement. So in case of our previous example, when our dependent variable was income and our independent variable was education, and if the beta value was say 500, just say, then that would mean, because our education variable was measured in number of years and our income variable was measured in rupees, simple rupees, not in thousands. Okay, so what this 500 would mean is, if the education increases by 1 year, the income would increase by 500 rupees. The increase or decrease would depend on the sign. So how are we attaching units with this? We are using the units of the independent and the dependent variable. But what would happen when we would change these units? So instead of, say, billions of dollars, what we did, we divided a whole series by 1000. So we divided our independent variable by 1000. All the numbers is in our independent variable, or the whole series was divided by 1000, and now instead of in billions of dollars, we have in millions of dollars. We multiplied it by 1000. So what we did, we changed the unit of the measurement. So now both our independent and dependent variables are in billions. So in that case, when we run the regression, what would happen? You would notice that the coefficient, the beta coefficient, the slope is exactly same. It haven't changed. The standard error is same. The r-square would always be same. In this case, when we changed both the independent and the dependent variable, in this case the constant term, the alpha term, had changed. And because we multiplied our independent and dependent variable by 1000, the constant term and standard error had also been multiplied by the factor 1000. But the beta coefficient would remain same, and if we look at it in its interpretation, then we would say that every 1 million increase in the GDP, the GPDI, the gross private domestic investment, would increase by 0.25 million. So in interpretation of the coefficient would remain same, but the constant term would change, but just the units would change. So now instead of 926 billion, we have 926,090 millions. Okay, so what if we changed one of them? In this case, if our GDPI is in billions and GDP is in millions, what would happen then? You would notice that the constant term would remain same, but the coefficient would change. And in this case, coefficient had been divided by 1000. So how would we interpret this? Because GDP is in millions, we would say that every 1 million increase in GDP, the GDPI would increase by 0.00025 billions. And you have probably guessed it, and if our GDPI is in millions and GDP is in billions, then what would happen is that the interpretation would be like, if the GDP increases by 1 billion, the GDPI would increase by 253 million. So 253, remember initially we had 0.25 billion, 253 million is equal to 0.253 billions, right? So just the interpretation would change. I mean, the effect wouldn't change. The interpretations would change, but the effect wouldn't change. It would still be the same slope. We would have the same shape of the curve. The slope would be same, but just the interpretation would change depending on the units of the independent and the dependent variable.